Good evening, everyone. Have you guys been having a great time at Otronicon? Woo! What's the coolest thing you've seen all day? You, right there. All right, him. He's got his hand up. What's the coolest thing you've seen all day? The Arc Attack, yeah? He was just talking about he's got to follow Arc Attack. You got to give him, like, extra applause for going after them, right? But he might blow up stuff in your mind. All right, anybody else? What else is the coolest thing you've seen today? This speech right now. It's the coolest one. All right. So tonight we have our keynote speaker. His name is Dr. Michael Gourlay. He has most recently worked as the principal lead software development engineer at Microsoft on HoloLens in the Environmental Understanding Group. I think that's a long title.
Yeah.
Well, anyway, everybody give a warm welcome to Dr. Gourlay.
Thank you. Thank you. And before we start, I really do want to get a shot of this. I'll explain in a second, but hang on. I got to act like I'm getting shocked. Okay. So that little camera right there, it takes a picture of everything. I'm just going to leave it there. It's a great complement to augmented and virtual reality because it takes a picture in all possible directions. So, all right, so I'm Michael Gourlay, and tonight I want to tell you about what I think is the future of augmented and virtual reality. And I'm going to tell you about a new way of thinking about augmented reality platforms, aside from what I think is the obvious way of thinking about them. And I'll close with a prediction about who is going to pioneer that new way of thinking about augmented reality. So, first, the story I'm going to tell you sort of is a meandering tale with some twists. And those twists will make more sense if you understand more about my story. So I'm going to tell you about that. So I'm shy. And as a shy child, I tended to have at most one close pal at a time. And eventually, that pal and I would part ways because I would change schools or whatever. And I always wanted to have persistent friends. And when I was a kid in the late 70s and early 80s, my mom would take me to the grocery store. Or she'd go grocery shopping and she'd either drop me off at the video arcade, remember this is the 80s, or I would hang out at the magazine aisle. And so that was sort of the formative features of my life, were video games and reading from magazines. And there was one article in particular that I remember reading, and this is as a little kid and it sticks with me today, and I was reading about this thing called Eliza, which is an artificial intelligence, and this is written in the 1960s, and so what they counted as artificial intelligence then, the notion of what counts as artificial intelligence has evolved over time. Eliza is a really simple text processing bot that acts superficially like a psychotherapist. And supposedly some of the people who tried using Eliza found it so compelling that they even revealed personal and intimate details to this bot. And I was reading this article about this, and I thought that was really interesting. In fact, the idea of interacting with a computer in this personal way, and this was a completely foreign concept to me, but that idea instilled in me an obsession that pervaded my life, and it continues even now. I wanted to interact with computers in this personal way, and I wanted them to understand me. And I wanted to create my own pal. So I bought an Atari computer, and most kids, when they buy an Atari, would buy games. I bought the programming pack that you could get with it. So back then, you could either buy game packs or programming packs. And it came with this book that was basically Teach Yourself Basic, which is a computer programming language. And that's how I started learning how to program. And I still have that book today, and it's great because it has like little kids scrawl and pencil, and answering all the questions that it asked. But after pondering artificial intelligence and toying with the idea, I perhaps naively concluded that in order to understand people, computers had to understand the world that we live in. And to get computers to understand humans, I first needed to get them to understand our environment. I didn't at the time have a lot of faith in the way that AI was going, which is I was a teenager, what did I know? And so that's in no way a statement about what researchers are actually doing. It was more about my own hubris. But what I decided to do was to study physics using computers. In other words, I wanted to get computers to understand the environment, and I felt like that was a route to that way of doing things. So for my doctoral study, I chose this computationally involved branch of physics, which is computational fluid dynamics. And it's hiding a little bit behind this Tesla coil, but there are some pictures down there of the kind of stuff that I did. So I learned about physics simulations using numerical algorithms, and I also learned about data visualization using computer graphics. And it turns out, I was a research scientist for a while, and I didn't enjoy certain aspects of academic research, so I left it to pursue another discipline that merges simulation with visualization, and that is making video games. So I joined Electronic Arts, and I made video games, including Madden NFL, which is here today. If you guys haven't seen it, it's up on the 4th floor. And at the time I was at EA, I interleaved that time to help start this program at the University of Central Florida called FIA, and they're also representing here today. In fact, there are some people in the audience and other people giving panels who are from FIA. FIA is a graduate program that teaches programmers, artists, and designers how to make games and other interactive simulations. So now I work at Microsoft on HoloLens, which is an augmented reality platform. Most of you are probably familiar with that term, augmented reality, and you probably have a pretty crisp idea in your mind about what augmented reality means to you. What I'm going to tell you is what it means to me, both today and more to the point of this talk in the future. The most immediately obvious aspect of augmented reality is that it lets you see holograms in the world. And so let me play this video and speak to it. So that's a really powerful, but it's a simple illusion, but it's very powerful. And so we have this boy standing there in Kyoto. And in order to pull off that illusion requires incredibly sophisticated algorithms, sensors, and computation. This video is from a colleague of mine who worked with me on HoloLens. His name is George Klein, and he made this back in 2009. And I believe this was either part of his doctoral research or, shortly thereafter. So I want to talk about certain aspects of this, because these are kind of the basics of AR. In order for us to believe in that illusion, there are certain aspects or certain properties that it has to have. First, it has to be locked to the world, which he was. And you'll notice that when I played the video, the camera was kind of moving around, but Cartman seemed like he was attached to the real world. Okay? And that world locking is a key feature. Second, in this picture, Cartman occludes the real world. Occludes just means he's hiding the things that are behind him. So we can't see the buildings in the ground that are behind him. So that piece of occlusion is key. And there's a third part, which is that he's not falling through the ground and he's not walking through buildings. So he seems to be obeying physical laws that we're familiar with. So there's another aspect, which I'm not going to show you in this picture, but I'll show you a little bit later, which is that real-world objects should also occlude him. And I'm going to return to those points in a bit. But there's another aspect of augmented reality besides this visual aspect, which is maybe less obvious, which is the question of how do users interact with augmented reality platforms. So a lot of us are already familiar with this notion of computers and humans interacting, and in case you can't read it, in that intersection region, it says computer-human interaction, and that's been a field of study basically since computers have been around. So it's been studied for decades, but I want to add to that. And the thing I want to add to that is the environment. So now I've added one element, and now there are, instead of 2 circles, there are 3 circles. But now instead of 1 overlap region, there are a total of 4 overlap regions. And some of these we're familiar with already, and some are new. So for example, in the overlap region between humans and environment, there is conventional reality. And that's the place where we like to live. Right? So there's another overlap region between computers and environment, and that is new. And that is a region that I'll call environment understanding. And that, in fact, is the group in Microsoft where I work. It's called the Environment Understanding Group. And when you combine all 3 of those together, you get augmented reality. So it's the intersection of humans, computers, and the environment. And it has in common that there are elements of human-computer interaction, conventional reality, and this new thing called environment understanding. So I want to tell you more about environment understanding. But first I want to familiarize with some of what I mean by this. This is a very abstract diagram and an abstract set of concepts, but let me show you some examples of what I mean by this. So this is a fictional one, but in a sense all of augmented reality is fictional, so I think it's legitimate. And in this scenario, we have an engineer who is designing something, and he's designing that in the situation where it would actually be used, and it's helping him visualize this. So let me show you another example of this. This is not fictional in the sense that this wasn't made by, this isn't a movie. This is well, it is a movie, but it's a movie not meant for entertainment. This is a guy who made his own augmented reality experience, and he's using a Kinect sensor to track his skeleton. And he's rendering on top of that a composited model which is stuck to his body. So this is another example of augmented reality. And there's another piece of this, which is, so what if you want to create an object in the real world? So augmented reality will help you do that. And it can help you do that in the space where the piece would end up. So let's watch this video. And notice what the user is doing is they're using this sort of paintbrush to create an object. And that table that's there, that's their actual table. That's not a virtual table or a synthetic table. That's their actual table. The only part of the scene that is virtual is the part inside of the box and the ball. The other thing that augmented reality lets us have is an infinite canvas. So we're used to having to buy monitors when we want more monitors, or just not having extra space. But with augmented reality, if we want more monitors or if we want more workspace, we just create it. And you can do that with a gesture. So augmented reality eventually gives us, effectively gives us unlimited virtual displays and an unbounded amount of screen real estate. It also lets us visualize things like how furniture would look in our apartment or in our personal spaces. And it could also capture the furniture that we have and let us bring it to a furniture store and see how things would go together. So AR lets us capture and visualize and manipulate things in a virtual way. It also lets us visualize things that are difficult to understand. So I love this example because it has personal meaning to me. These images depict concepts of vector calculus. That's not an approachable subject. In fact, the words vector calculus, that's not even an approachable pair of words. What do those words even mean? Some people probably haven't even heard those two words before. And first, when I was learning them, I struggled to learn these concepts, and later, when I was teaching, I struggled to teach them. The concepts are very abstract, but visualizing them makes them concrete. Now, maybe from this picture you haven't already understood what vector calculus is, but trust me, looking at these pictures does help when somebody is giving you sort of the mathematical formula behind them. And if you can give a concrete visualization and you can make interactive virtual simulations with them, you can make them fun and interesting. And interest is a key to success in education. I think that one of the key parts of education isn't answering questions, but instilling curiosity and making people ask more questions on their own. But there's another school of thought that says that these hard-won concepts should remain elite and hard-won. So I'll let you read this panel. So that's a cartoon from a cartoon called Saturday Morning Breakfast Cereal. Augmented reality also lets users communicate with each other remotely in more compelling and personal ways than ever before, using holographic telepresence, and we've seen examples of this over and over in the movies. And AR would allow things like this. So those were just some examples of augmented reality that weren't just the basics of rendering holograms into the world, but also involved some aspect of interaction with the environment. And so I mentioned engineering, art, productivity, design, education, and communication. And I'll give some more examples later. But next I want to talk about an important concept, which is reality. So I've just showed you examples of augmented reality, but I want to contrast that with another kind of reality. So if you know anything about either augmented reality or virtual reality, you probably think of them as similar. Maybe some of you don't even make the distinction. After all, they both have the term reality in them, and they both have headsets that let you experience them. So what's the difference? One is augmented and the other is virtual, right? So that's the difference. So, but what does that mean? There's a more fundamental difference, though, between just the difference between augmented and virtual. And that is the fact that the word reality in those two phrases actually refers to a different thing. So not only is augmented not the same as virtual, but the reality in augmented reality is not the same as the reality in virtual reality. What do I mean by that? Well, virtual reality is a completely synthetic alternative to reality. Whereas augmented reality is our reality, this reality, but enhanced in some way. So that might be kind of a subtle idea, but what I'm really saying is that that word reality doesn't actually, it's the same word that has two different definitions. And if you think about swapping the words augmented and virtual in other phrases, I think you'll start to understand what I mean, that they're talking about two completely different things. In virtual reality, you're replacing reality with something else, and that something else is more iconic. By iconic, I mean it is an abstract representation of the real thing. And just like this progression of pictures at the bottom shows, which is taken from a book called Understanding Comics, we go from something that's realistic and distill it down. Now that has power, but it's different. So virtual reality requires that you replace the entire world completely. Even if you leave it empty, you have completely created an empty world. It's also the case that when you create a virtual reality experience, you're responsible for creating all of the rules that make that reality happen. Now, you can try to make them seem like our physical laws, and a lot of games do that, but you are also given the freedom to create impossible scenarios and create physical laws that don't actually exist or are not possible. Also, virtual reality is not constrained by real-world content. Not as much, anyway. But it is the case right now that when you're immersed in a VR experience, the user can't see the real world. That's by design. But it also means that they can't really navigate the space that they're in. So if you're in a cluttered environment with a VR headset, you could hurt yourself if you're not careful. And that's kind of, but the point is that when you completely replace the real world, that's both a benefit and a hazard. In contrast, AR builds upon big R reality. So augmented reality, first of all, reality has a lot of pre-existing content. And it would be a shame not to exploit that. It's like the ultimate turbo squid, if you know turbo squid. But AR platforms encourage the users to explore their environment so they can walk around. And it also means that developers for AR content are very strongly encouraged, if not required, to exploit that pre-existing content. In other words, they have to incorporate the real world into that AR experience. And for example, they need to lay out a play space. So for example, if I wanted to play a game on this stage, I would somehow have to have a virtual representation of the layout of what's here. And if I wanted to build a platformer, like a little character running around and jumping maybe on top of this platform and so on, or maybe down off the stage and down there, then the simulation would have to know something about that environment. And this is where it gets interesting. When you're building a VR experience, you generally just build whatever you want. If you want a big flat plane, you have a big flat plane. If you want slopes and platforms, you can just build those. If you're building an AR game, you have to take into account the stuff that's there. And not only do you get to use it, but you have to use it. So a lot of the level layout, the design of the game, has to be built into the game itself, rather than being pre-built before the game is shipped. So that's really cool. It can be daunting, but it's also really amazing. So I'm going to talk more about, right, and the other thing is, aside from that virtual model of the real world, you also have to have a virtual model of not just the geometry, but also of the rules that apply in the real world. So you have to have a model of the geometry and the procedures, or stated differently, of both the data and the algorithms. And that is what I mean, that's part of what I mean by environment understanding, is acquiring that, first the geometry, and also expressing the rules that you apply to that geometry. So I want to frame this concept of environment understanding within this existing paradigm. So before I mentioned human-computer interaction, I want to describe that in this kind of simplistic framework. So this diagram shows the simplistic framework where real characters on the right represent humans, including users, and the virtual nodes on the left represent computers. And the arrows here represent modes of interaction. And so I want to do something like I did before, where I want to add one more node, which is the real environment. And then notice what happens when I draw all of the links, is that I get twice as many. So in other words, with just computers and humans, you had a certain number of modes of interaction. When I add the real environment, I double the number of possible interactions. So again, this is the kind of stuff that I want to talk about, when I talk tonight about what I mean by a new way of thinking or a different way of thinking of augmented reality. It's not just about rendering holograms. It's also about this new way of interacting with computers. So I'm going to show some examples of what I mean. So earlier I mentioned that Cartman was occluding the real world. And I said that I couldn't show it in that picture, but I'll show it later, that the real world also has to occlude the hologram. And so here's an example of this. It's kind of a subtle example, so I'll show a more clear example in a moment. But notice here that you have this virtual teapot in this real hand. And just like before, the handle of the teapot is occluding the user's fingers. But also, the user's thumb is occluding that bottom part of the handle. In this picture, it doesn't seem that impressive. And in fact, we're so familiar with it, it seems pedestrian. What's the big deal? Well, it's actually kind of amazing, because in order to pull this off, you have to have this representation of the real world in the computer, and it has to be very responsive. And that's pretty cool. So this video shows another example that I think makes it a little bit more clear. So here a user is standing in front of the hologram and occluding it. Now he's behind the hologram occludes him. And we go round and round. And then he'll go around the back of the hologram. And both of those modes will occur simultaneously. So he's being occluded by the hologram, and he's also occluding the hologram with his hand. So that's awesome. And this is one mode of interaction that is purely visual, and it's bidirectional. And that's really cool, but it gets even better. The interactions can go beyond just rendering and visual. They can also be physical. In this simulation, the virtual elements, which are these yellow balls, are interacting pseudo-physically with the real world, which is the table and the floor and so on. This is amazing. So let me show you some more of this video. This is a video from another colleague of mine, Shahram Azadi. We work together on HoloLens. And so in this case, the AR platform requires not only a geometric model of the real world, which is already amazing, but it also has to have a procedural model of how to simulate the physics. Lots of games have physics engines and can already provide these physical interactions between virtual objects. Or a virtual object interacts with another virtual object. Here, virtual objects are interacting with real objects. That's very, very cool, and it gets even better. Virtual objects can also respond to changes in the real environment by real people. So this is the complementary modality of what I just showed you. In this example, virtual objects which are mobile are responding to real objects which are also mobile. In the previous video, the real objects were stationary. In this example, they're mobile. So let's look at this. So the balls there are virtual and the hands are real. And so the user is picking up these balls and manipulating them. This is another bit of research by my colleague Shahram and his colleagues. There's another thing that augmented reality can do with the environment, which is to let you visualize things that were otherwise invisible. Wait, what? Okay, so here's an example where we're using augmented reality platforms which can sense things like Wi-Fi radio signals and then let us see them by adding a rendering on top of the real environment. So that's pretty cool too. And it gets even better. But before I explain what gets better, I want to take a detour to talk about how this thing in environment understanding works. Because understanding how this works explains what comes next and why it will happen. And this is where I take a little bit of a left turn, and I'm about to blow your socks off. So grab them, because there's going to be a big sock pileup. Okay. So augmented reality is a combination of 3 parts. One is the algorithms that let AR platforms understand the environment, such as tracking the pose of a headset. Another part is the output of those algorithms, which is, for example, a stream of rendered images. And the third part, which I'm leaving last because it's the sort of climactic thing, which is the inputs. And this is when I mentioned at the beginning of the talk that I wanted to talk about a new way of thinking about augmented reality. We're used to thinking about the outputs, but the inputs are what's really enabling for some really cool stuff that augmented reality platforms will eventually be able to do that probably not very many people are thinking about right now. So the thing is that augmented reality platforms, in order to pull off that seemingly simple but powerful illusion of world-locking holograms, has to have this amazing array of sensors. It's not showing up awesome on this slide, but that thing on the left is an exploded view of an augmented reality platform called the DAQRI. And it has crazy amounts of sensors on it. So here's another shot of it. And I'm going to zoom in on it. And again, it's a little bit blurry on this image. But what I'm zooming in on are a cluster of cameras. And in this case, one of the cameras, the one at the top, is a depth camera. And a depth camera, so this is kind of cool, but I think people get so used to new technology, no matter how mind-boggling it is, they're like, oh, I heard about that yesterday. That's normal now. But there's a new kind of camera, new in the sense that it's been around for about half a decade. And it's able to sense depth. And this is what it sees. What this is a picture of is depth. The dark regions are closer to you, and the brighter regions are farther from you. And in this picture, you can already make out certain things. You can see a person there on the right, and you can see a chair in the middle, and then another maybe couch, something on the left. It's hard to see what's going on above the couch, though. We can't see it from this picture, but I want to show you what you can do with these depth maps. You can fuse them together. You can take multiple depth maps and their poses, and you can fuse them together to make a model of a room or of a scene. And so in this picture, it's starting to become a little bit more obvious what's going on. That blobby thing above the couch now is starting to look a little bit like a bookshelf. In fact, it's an Atari collection. And you can see some other elements. And the thing is, this isn't just a recoloring of that previous image. It's just one perspective, but we can take other perspectives. So if we pull out and tilt up and zoom out a little bit, this is another perspective of the same scene. So you can see the person, the chair, the couch, and the bookshelf. And we can zoom out even further and see that in the context of a living space, and zoom out even further, and you can start to see the whole living space. Okay. This is part of the magic behind the interaction between real and virtual worlds. This is the geometry part that I mentioned. And this is the thing that lets AR platforms have real and virtual objects both occlude and collide with each other. That's pretty cool. And it gets even better. Starting with this geometric model of the real world, what else could an AR platform do? Well, let me show you, that was a couple of images. Let me show you a video that I hope explains this better. So this is Shram again. He's picked up a Kinect, which has a depth sensor, and he's going to walk around this room. And the upper left is the depth image, the instantaneous one, and the bottom 2 images are the fusion of all of those depth images together to build a geometric model. So I'm going to play that again just to let it kind of sink in. Upper left is the depth map. Lower 2 images are the model that's being created. So as he walks around the room, a bunch of depth maps, and then notice that there's this geometric model that's getting sort of painted in as he looks around with the camera. That is called surface reconstruction. And that's one of the teams that I lead at Microsoft. So again, pretty cool. And this is what enables us to do the occlusion and collision. What else does it let us do? Well, it can also help the computer understand the environment in more sophisticated ways. For example, it could help a user navigate a space. It could also help a virtual character navigate that same space. So if the computer has a geometric model of a space and it understands the idea of connectivity or passability, you know, like what can you navigate or navigability, it can make up rules about, well, a person or a virtual character, which to a computer, what's the difference? They can say, okay, a virtual character can go down off the stage and, you know, through that doorway or up the steps here. Wouldn't be able to go through the wall. Wouldn't comfortably be able to climb the chairs, right? So, what could you do with that? Well, what's the difference between an autonomous vehicle and a virtual vehicle? If I can get a virtual vehicle to navigate a space and I can make a really accurate physics simulation for that virtual vehicle, and by really accurate I mean it's obeying physical laws as we understand them, and I'm going to apply control signals to that virtual vehicle like thrusters or other control surfaces, then the difference between that virtual vehicle and a real autonomous vehicle is very slight. I can apply the same control signals to an actual vehicle, and it can go and navigate the real world. So, in fact, that's not really different from what autonomous vehicles actually do. Is an autonomous vehicle has a model of itself, and it's applying a virtual simulation to that model of itself, and then it's taking the signals that it's applying to that virtual vehicle and applying it to its own actuators. And it flies around. So let me, again, make this a little bit more concrete. So I used to explore caves, and that's a very dangerous and uncomfortable sport. And I used to actually not just explore them, I would survey them. And I did this for the US Geological Survey. And I'll not bore you with the details of how you did it, or how one did it, but I would always be in the muck, in the dark, in the cold, with these precise instruments and taking these measurements, looking through these special kind of telescopes and so on, and thinking to myself, man, it would be great if you could just walk around and look at this and take a bunch of pictures and it would make the map for you. And then this movie came out. Maybe some of you have seen it. It was called Prometheus. It was the prequel to the Alien movies. And here's a segment from that. So at one point they go into this vast cavern system, and this guy tosses these drones into the air, and they go flying around, and they build this map of that cavern. Did anybody see that movie? See this? Okay. So I thought, oh, cool. Ridley Scott had the same idea I did. And he made a movie out of it. But we'll never do this. And then I started working on HoloLens. And it turns out, so check this out. So this is a drone that has a depth camera on it and a few other cameras. And then the upper right is the drone flying around, being chased by a grad student. And then the upper left is one of the cameras that's on the drone. And then the middle is the environmental model that it is creating, using essentially the same technique that Shahram was using with the Kinect, except that Shahram is holding it and waving it around. And in this case, the drone is flying around. And the drone both has to do this because it needs to know what not to fly into. But as a side effect, we get a model of this environment. And this could be pretty useful in a lot of situations. Okay, so these autonomous quadrotors could be sent to dangerous places and map them out, and then remotely send us back this signal. Right? So that's pretty cool, and it gets way better. What else could AR platforms do when they understand the environment? So before going any further, I want to recap here and talk about these. So I originally talked about these basic modes of augmented reality, such as occlusion and rendering and world locking. And then I talked about how augmented reality incorporates the environment in a few ways, such as occlusion, collision, manipulation, visualization, reconstruction, and navigation. The top three I would call sort of intermediate modes, and the bottom three are starting to get into modalities that help us understand the world ourselves better. In the first case, we could start to see, it was like augmenting our senses. We could start to see radio waves. And in the last two, it helped us see the world that we live in from a different perspective, which is always very helpful. But what else can augmented reality platforms do for us? And where is it headed? Well, imagine that after we have this geometric model, we can formulate another kind of model. So here's an example where there's an augmented reality app that is showing a user how to repair some part of an engine. So the augmented reality platform knows where the various engine parts are, so it knows where to direct the user's attention, and then it can give instructions that are appropriate to the context to the user. That's pretty cool, but it presumes that the computer not only has a geometric model, but it also has another kind of model. And I'll give it a name in a second. But the point is that if it has that other kind of model, then it can help us understand the environment in a way that the computer does. So now the computer has some sort of understanding that we lack. I don't know how to, I don't even know what he's doing. I don't know how to repair that thing. It looks like a fan, maybe, some kind of turbine. And the computer understands it, and it's going to enhance my own cognition because the computer has precognized this for me. That's pretty cool. So, but we need more than just this geometric model. We need a semantic model. The augmented reality platform would need to be able to segment these pieces of geometry from the world and then label them with their names. Before I talked about, I showed you these models of the real world, we saw chairs and people and couches and bookshelves. But the computer at that stage just saw triangle, 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 little pieces of geometry. But we can take it a step further and semantically model this. And how did we learn to segment the world up into little pieces? Generally, by somebody, usually our parents initially, pointing at or touching something and saying its name, right? So can we do that with a computer? Look at this video. Oops, I have to click on it. So here a user is going to put his foot on the floor and he's going to say the word floor. And then the computer is going to infer that the floor isn't just that one arc, it's everything that touches it. Then he goes and touches the chair and says the word chair. Notice it's a different color, so it's segmented from the world. Now he says table, and now he's going to circle the banana and say banana. Now he's going to label the cup. And then when he pulls back, the other chairs are also going to be recognized as chairs. So what's going on here? There's a lot going on here, right? That's amazing. And this is not faked. This is something that we can actually do today. In fact, the same researcher whose name I've said over and over, Shriram, and his team have done this. So they've combined this geometric model, and now they've added to that a semantic model. And at this point, again, we're probably already bored with the idea that computers can understand our speech. That's pretty amazing, too. I'm not going to talk about that today. But really, all they did in this, all that they did, I don't mean, all that the user in the video did was say things like table or lectern or chair or whatever, and the computer started to infer this. The video goes on, and so it can generalize to more than just that one shape of chair. It has a sort of dictionary of chairs and all that. But the point is that the AR platform can learn this stuff just by doing what we did as children, which is to look and to listen. Now, of course, there's an awesome algorithm behind all this. But the thing is that allowed this to happen, one of the key ingredients was all these inputs, this amazing set of inputs that are part of an augmented reality platform. There are already apps out there where, so there's a real sign in the background, and in the foreground is an augmented reality app that translates that sign in situ. So you could imagine if that phone, instead of being a phone, was a headset, what the user wearing the headset would see was a sign in their own language. Right? So this is another example of a semantic model of the real world. But this is different. Before I was talking about geometry, and geometry is very concrete. In this case, the shapes here are abstract. There is no inherent meaning to a letter other than what we ascribe to it. the thing is, so this is symbolic semantic labeling before it was geometric semantic labeling. It turns out this is a little bit more in the comfort zone of a computer. This is symbolic manipulation, and computers are actually better at dealing with symbolic symbols than they are with other things. It turns out, so people are also good at manipulating symbols, so that's something we have in common, right? Computers and humans can both manipulate symbols relatively well. What is the most evolved form of symbolic manipulation? Let me back up a step. So what do I mean by a symbol? First, I started talking about geometry, like actual couches and shapes and so on. Now I'm talking about symbols. So what is a symbol? A symbol is a sign or some kind of an abstraction that stands in for something else. So when we manipulate a symbol in our minds, what we're doing is we're manipulating a class of objects, not just an individual object necessarily, but a whole class of them. So what do we call it when we take that to the most evolved possible level that we're aware of? The answer is thought. Conscious verbal thought. So I got through that whole section about geometry and flying and so on, and your socks are still on. And some of you are probably thinking, what's the big deal? I said I was going to knock your socks off. Well, what I'm saying is augmented reality is far more than drawing cartoons on your wall. It is a stepping stone to autonomous computer agents and general artificial intelligence. And the reason is, this is going all the way back to the beginning of my talk, in order for computers to understand us, it has to understand first our environment. And there are a few ingredients to this. That's a fairly bold thing, right? Like I just took a huge leap there. Everything else I kind of guided you step by step to something. So I want to give you a recipe for what it would take to create this generalized artificial intelligence. First, you have to have a unified theory of cognition. That's a different talk. So I'm going to move on. Next, you have to develop deep machine learning algorithms. What do I mean by that? Well, I don't know if you guys noticed, but around 2009, the ability of computers to understand our speech went from, you would go on these really awkward telephone conversations where it would say, if you want to talk to blah, 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 say this word. And then you'd say that word, and 90% of the time, well, it was probably more like 70%, or like 30% of the time it would get it wrong. But to us, it felt like more like 90% of the time it got it wrong. And we would say this, and eventually we'd start cursing into the phone, and it would, either recognize that we were cursing and take us to an operator, or we would hang up or whatever. But around 2009, things started to get better, like drastically better. I don't know if you noticed that, but it is actually the case. Like numerically, people have been able to, computers have been able to understand people a lot better since then. So what changed? You remember when Siri came out and everybody was making, a big deal about Siri? Just as an aside, this has nothing to do with the rest of the talk. Does anybody know what technology powers Siri? Dragon. There are two parts of it. Well, just really one. The answer is Bing. It's the search engine that everybody loves, but actually it's Siri. And Microsoft powers Siri, and Microsoft also powers Cortana. So, and Siri is often held up as this thing that's it sometimes makes mistakes, and the mistakes are always hilarious, but so are the mistakes that children make. There are a lot of videos. Has anybody seen the Pwinkowin video? Nobody? Crickets. Okay, that fell flat. There's a great video about these kids arguing about whether or not it's waning or pwinkowing. It's awesome. So the point is, it's kind of cute when nascent consciousnesses get things slightly wrong. And that's sort of where Siri was a while back, and it's getting better. But the point is that what changed was our ability to train neural networks and other technologies like that. And the moniker that people have given that new wave of machine learning is called deep machine learning. I won't really go into it other than to say, if you remember neural nets back in the 80s, and you remember how in the 1980s everybody was talking about how great neural nets were, and then we stopped hearing about them for a while. And now we're starting to hear about things like deep neural nets. I mean, maybe not all of us are, but some of us are hearing that. And so this notion of deep machine learning is starting to come up. And there were a few major ingredients. One was there were new algorithms created to help teach neural networks. Another one was the computational power of training neural networks absolutely exploded. And part of that is because of cloud computing. And that's a key ingredient. And I'll come back to that in a minute. But the other thing that you need to train these things is vast amounts of sensory data. So one of the key ingredients, remember, there's a new algorithms for training. Another one is vast amounts of computational power. But the third ingredient is vast amounts of sensory data. Why did voice recognition start to become really good all of a sudden? There was another thing that started to happen around the same time. One example of that is Google Voice, which is basically Google let people start using Google services to talk to each other. Instead of using a phone, you would use Google Voice. Why would they do that? So that they could get vast amounts of sensory data, so that they could feed these gigantic clouds of computers with these new algorithms. So what else acquires vast amounts of sensory data and is always around? Yes, and also augmented reality headsets. They will soon be very common. They'll be seeing what you see, they'll be hearing what you hear, and they'll be connected to a cloud. And in the cloud are where the learning algorithms are. On your face is where the data is coming from. So those last two things right there, the deep machine learning algorithms and acquiring vast amounts of sensory data, are coming very soon. And this is what I'm talking about as why this is headed in this direction. So I already mentioned the cloud. You need a cloud because cell phones are great at acquiring data and they're great at providing you a certain amount of input. They don't have a huge amount of computation built into them, but they do have an internet connection. So if they can stream that data back to the cloud and the cloud can chew on it, then the cloud can learn. And that's what's happening. Okay? There's really the one last step there, sentience. So it's like I'm trying to remember the... Skynet? Well, Skynet, yeah, but I was thinking, there's the recipe for the underpants gnomes. Step 1, collect underpants. Step 2, iconoglossary. And then step 3 is profit. So this is this really, really simple recipe that I fully expect that all of you have completely bought into at this point, right? Because I've explained it step by step. I don't know what could be missing. But there's a few things I wanted to point out, which is who has massive cloud infrastructure, who has augmented reality platforms, and who has made huge investments in deep machine learning algorithms. So I'm sort of I'm foreshadowing. Because I mentioned at the beginning, I said I'm going to give you this kind of amazing view of where augmented reality is headed, and then I'm going to give you a clue, or give you my answer to who I think is going to pioneer this. But anyway, the pieces are all there. I didn't say anything about unified theories of cognition because it's way outside of the scope of this talk. But I talked more about the middle three, and I'm claiming that the pieces are there, and that we just need somebody to assemble them. I'm oversimplifying a little bit, but I don't think it's that far-fetched. What I'm going to get to is really far-fetched, but I don't think this part is. Okay? And so what happens when we put that together? Well, one of the things that we can have are virtual companions. Now, virtual companions are more plausible when they can be next to us and when they don't fall through the ground and when they can interact in a way that is, believable or plausible. And I seem to have come full circle, right? I started this talk by saying I wanted to build a virtual companion. And I've gone through all the steps of what I think are the necessary ingredients, and I've also made the claim that all these ingredients are here. We've got vast amounts of sensory data. We've got the algorithms that know how to learn from that data. And we have cloud compute that has the horsepower to run those. But what could be better than having a virtual companion that was next to you? This is where your socks come off. Neural interfaces. So imagine that your virtual companion lives inside your head. Now, take it one step further. Your virtual companion, who is connected to the internet, and who has all these amazing sensors, including things that we don't have, and they can talk to you inside your head using your own voice. So now your virtual companion becomes part of your own inner dialogue. Does that seem far-fetched? I mean, it would take a serious amount of funding to make that happen, right? So who is funding this? DARPA, the Defense Advanced Research Project Administration, has a program called Reliable Neural Interface Technology. Not just neural interface technology, but reliable. The National Institute of Health has a program called the Neural Interfaces Program. It's not a project, it's not a study, it's not a paper, it's a program. If you're not familiar with the term, that means that they're not just looking to fund one person. This is a thing that lasts across many funding cycles. They have a budget, which is far more, they have a budget. On top of everything else, there are already commercial products that you can buy today that are neural interfaces. And in fact, the pictures that I have up there are available for purchase. And you can play with them right now. And one of them is this company called Emotiv. By the way, no connection. I don't know anything, I don't know anything about Emotiv personally other than what I've seen. So no endorsement implied. But they're just one example. And they gave a TED Talk where on stage, the speaker brought up an assistant, and the speaker had this device on his head. By the way, no gel, no goo, no drills. He just put this on like a hat, okay? And he stands up in front of a computer like this, and then he's looking at a cube, and he's asked to think about the concept of pulling. And then the lady presses a button, and so he's standing there thinking about the concept of pulling. And so what's happening is that the sensors are feeding into the computer, and the computer is trying to figure out what is the pattern in this signal coming from his brain. So he says, okay, I thought about pulling. 8 seconds go by. She says, okay, we've finished training the computer. So 8 seconds later, the computer now knows what it means for him to think of the word pull. So then it goes into usage mode. And he thinks about the word pull, and this cube comes toward him. This is after 8 seconds of learning. Then they add to that vocabulary another concept, which is disappear, which is really hard for us to imagine. We can imagine pulling because we do it. Imagining disappearing is really tricky. Nevertheless, he did it, and with some difficulty, he was actually able to train the computer to understand the concept of disappearing, and he was both able to pull the sphere and then or cube, and then make it disappear. So that's a vocabulary of 2 words. They claim they can have a vocabulary of up to 8 words and 13 gestures, who can also read facial expressions and so on. So we're up to, in the sort of dozen-ish range. How far do we have to go before we can get to a full vocabulary? Well, a typical adult can have on the order of tens of thousands of vocabulary words, and we're up to about a dozen. We have a long way to go. Does anybody here remember or know how much memory an Atari 2600 had? $26K? 26 kilobytes. Anybody else have any other guesses? 4 kilobytes. The actual number is 128 bytes. That device created this industry. With 128 bytes, home computers and video games were created. Okay? Now, we're not quite at the point of having 1 billion times as much data. Actually, sorry, I take that back. This device has 256 gigabytes of persistent storage on it. So it's actually a factor of 2 billion. And it went from being something that plugged into a wall to something that's been unplugged for all day, and I'll probably go into halfway through tomorrow before I have to plug it in again. So in other words, from 1974 to 2016, we went from 128 bytes to 256 gigabytes. So we've gone from, right now, these neural interfaces can differentiate between about a dozen different, let's say, vocabulary words. And all we really need to get to is a few tens of thousands. I'm pretty sure that this is going to happen in my lifetime. So once we have neural interfaces, and they're bidirectional and all that sort of thing, you'd be able to wear a holographic computer on your face today that has something close to this capacity. Now, neural interfaces have a long way to go, but as I've just pointed out, that's not really an indication of how quickly they'll get there. So I think that this is where all this is headed. We're going to start with augmented reality platforms that we have this year, and we're going to end up, I think, right here. So, socks? Is anybody? Boom, they just came off. Right. So that's my vision of where this is headed. Now, just to recap, so I mentioned just in this past segment a few new things that augmented reality platforms will be able to help us with. And they include instruction, recognition, translation, cognition, companionship, and ultimately integration with ourselves. And here's a recap of all the things that I talked about during this talk. And this is just to kind of remind you, in case it seemed like I just covered a few things here and there. These are some of the examples. And for every one of these examples that I showed you, I have personally, myself, seen and used about a dozen different prototypes of experiences for everything that's on here. I have personally seen hundreds of cases of things like this. Maybe not so much at the bottom. Those are a little bit more advanced, but all this stuff up here, it's just around the corner. So, one last thing. I promised to tell you who was going to do this. So, before I answer, I want to make an observation and then ask you a question. The observation is this. I've talked about funding, and I've talked about, like the fact that there's been investments made and so on. But way more important than that are our skill set, the desire to do things, and a strategy that combines those things together. And without those three things, skill set, desire, and strategy, money and power don't matter. Money and power are tools, they're not the motivation. And companies only matter to the extent that they have people that have the skill set, the desire, and a strategy that puts them to work. So if you have the desire, I think everybody in this room has the capacity to learn that skill set. And this whole conference is about learning. And so if you're here, I think you've already demonstrated that you have that desire. And if you've noticed that there's more than just you in this conference. So you also have the ability to collaborate with like-minded people. And together you can formulate a strategy and then accomplish whatever goals you want. So I just described this vision of augmented reality, which is really, really far-fetched. That's a good thing, because no one's doing it right now. It's a wide open field. And right now people are thinking about, what can I do with these headsets? What can I do tomorrow with them? What can I do with them next year? I'm asking the question, what can you do with them in 20 years, or 30 years, or 40 years? Okay? So the people who I'm addressing really are people who are going to be playing that far out. Now, the thing is, I showed this crazy recipe, and I left some exercises for the audience. Unified theories of cognition and so on, just a little. I mean, I already know. I just want to make sure that you do the homework and figure it out. But the point is that if I've done nothing else than make you curious, then that's great. Because figuring out the answers to these questions is going to be the most important part of putting this thing together. And it's also the fun part. If this were already possible, like let's say that the culmination here was, ta-da, Microsoft is making neural interfaces, that would have been everyone would have really been surprised, I think. But a little disappointed, right? Because that would mean that you don't get to do it. And that's really what I'm trying to do, is get people interested. So I want to see who in the audience thinks that this crazy vision that I just cooked up is interesting. And of the people who are raising their hands, who among you wants to actually help make this happen? And stand up if you think that that is something that you might want to do. Okay. So look at this diagram. And you might have some thought about what I think I'm going to say is who's going to make this happen. But the answer is that you are. You have demonstrated that you want to make this happen. You're here. You're capable of learning. Your curiosity is piqued. Look around you. The people who are standing are going to be the people who collaborate on this. You're going to make this happen. It's totally plausible. It's totally possible. The ingredients are there. Now go and do it. So also, while you're standing, you can actually make a note of who else is standing and get to know each other. But that's really all I want you to do, is collaborate and learn. And the rest will fall out naturally, because you will be completely compelled to do this and just to keep going until you have another you inside your own head. Okay. So that's the end of my talk. I would like to know, do we have time, if anybody has any questions?
Yeah, I think we've got time, and we've got a question, so if I've got a mic, I've got a mic.
Hello, Dr. Gourlay. I actually met you earlier from Herculean Tech. So we have the visual aspects and the neural nets and stuff like that, but what we are working on is the actual feeling, the other half of the equation, the haptics and the force feedback.
Yeah.
And, you know, it would be great to also get people to start thinking on that side of it as well, because you have the virtual reality side. You know, you're in virtual reality world, and you reach out to grab a water bottle, your hand goes right through it because there's nothing there.
So let me echo that in case. Sure. So there's actually, I want to first acknowledge, yeah, I left out haptics completely. If you don't know what haptics are, it's basically force feedback or other tactile sensations. So you can imagine, so you have displays for your eyes, speakers for your ears, and then haptics for your sense of touch. And I believe that haptics are definitely they're definitely one of the stepping stones to the future, right? Mm-hmm. Absolutely agree. And I think haptics are another area where we're gonna see that, and it's gonna make things super duper amazing.
Other questions? I'm sure there are some. I got one down the front.
Hey, how confident are you now in the learning algorithms themselves?
How confident am I in the learning algorithms themselves? The answer is that they're already being used. So I'll interpret that in two ways. One of them is, how confident am I that they work right now, and how confident am I that they are going to go to get better? That they're sufficient for this crazy idea that I have of conscious verbal thought. So first, I'll tell you how they're doing now, which is that their ability to recognize speech is about on par with our own. You don't probably think that that's true. Like maybe a lot of people say, no, the computers can't understand me as well as a human can. That's actually false. That's demonstrably false. The reason why you don't feel that way, though, is that when you're having a conversation with someone, you won't notice it, but many, many, many times during that conversation, you'll say, huh? Or what? Or, excuse me? And they'll repeat themselves. The thing is that we have this built-in error correction algorithm, which is to say, huh? And then the person just repeats themselves. Computers don't have that. So their ability, like in other words, if they don't understand us right now, they don't say, I mean, they might say in this very long-winded way, I'm sorry, could you repeat yourself? You know, it's just like totally uncomfortable, and it's like, I get it, you want me to repeat myself. And then there's just like pause, and then a ding, meaning, okay, now you can talk. And by then you've already said no 4 times, or yes, or whatever it is, you know, like you said one word and it got it confused, or somebody was talking in the background. So my point is that that is already the case. And here's another interesting one in terms of, this is awesome, in terms of understanding writing. So you've probably all, if you've gone to a website, a lot of websites have this thing called CAPTCHA that says, prove you're not a robot. And so it asks you to type something in. If you've noticed over the years that what it's had you type in has evolved, and I'm not just talking about it got noisier or wigglier or whatever. There was one phase of this where what they did was they showed you two things, like maybe a word and another word, or a number and another number, whatever. Does anybody remember this happening? Mm-hmm. And it would have you type in both. Here's the thing. It knew the answer to one of them. It didn't know the answer to the other one. It was crowdsourcing optical character recognition. So it was doing two things. One of them was, so Google has this thing where they're digitizing a lot of books, and they run OCR on them. Every once in a while, it comes to a rectangle of symbols that it doesn't understand. It sort of pays CAPTCHA to find out what they are. CAPTCHA integrates that into that stream, and it asks hundreds or thousands or whatever people, here's the thing that I know, here's the thing that I don't. If a lot of people agree on the part that they don't know, they sell that answer to Google in the form of, here's what these three characters are. It's actually the word and, or whatever, right? So that's a great example of machine learning. And, so that was one part of it. So CAPTCHA sold the answer, but then they also used it to train their algorithms. Another answer is, real quick primer on how machine learning works. The idea is that there's a function that it's trying to optimize. That's a lot of whatever that means, right? But that function that it's trying to optimize is called a cost function. And a cost function is basically a way to quantify error. So here's an example of where machine learning is being used all the time. When you search for a term, let's say you're using Bing or Google, you get a list of possible answers. If you click the first one, that's the lowest possible error. If you click the second one, that's a slightly higher error. Click the third one, that's an even higher error, right? So every time you use Google or Bing, you are training it how to be better. So here's an interesting feedback loop. Why does this is the part where I wish I weren't being live streamed, but why is Google so good? And the answer is because it has the best algorithms. Why does it have the best algorithms? Because it has so much data to feed them. Why does it have so much data? Because it has the best algorithms. So it has this virtuous cycle of the more traffic it can draw, the better it can make the algorithm, which feeds more traffic, etc. They've created this massive barrier to entry. If somebody wanted to come up with their own algorithm, the algorithm is actually simple. It's like a little bit of math. The hard part is training it and getting this algorithm. The algorithm isn't actually the hard part. It's really the training. So there are three examples: speech, handwriting, and basically asking questions and coming up with answers, where we've already demonstrated we can do better than people in some cases. We can do about as good as people in others. And, can Google answer questions really well? Yeah, so can Bing. As long as you phrase them right. Like, we just rely on them. We take them for granted. If you were using search engines back in the mid-90s, the delta between, like, Alta Vista and Yahoo and all that, and then there was Google, and that was it. Like, it was all over. So that's machine learning. So I have a huge amount of faith in what it can do. In terms of what it will be able to do in the future, I know this is a very long-winded answer, but you asked a very, very deep question. There are two schools of thought in terms of machine learning. One of them is called connectionist, and that's where this deep machine learning stuff comes from, and that's where neural nets come from, or that's where they fit in. The other kind is called symbolic. And that's the school of thought that says the way that we think and behave and all that is a set of rules. And the best way to learn those rules is to ask people what rules they use, or more to the point, ask experts. And so they create these symbolic databases instead of these connectionist ones. And I think that, I talked about unified theories of cognition. I didn't say what it was, but I think that in order to get to real general machine intelligence, we have to have probably some combination of that, and also models that we don't talk about right now. So I think that these neural nets and other machine learning algorithms will be a fundamental building block, but I don't think they're going to be the end. They're going to be the start, and there's going to be some stuff in the middle, and then there's going to be, the crazy stuff I talked about. So I have a huge huge amount of confidence that they will be a building block. I don't think they're going to be 100% of it. So that's my answer to that.
All right, I think we have time for just one more question. So if I have somebody who hasn't asked a question yet. All right, back to you then.
All right. Sorry, so just for the sake of argument, I'd like to ask this question to you. So I'd like to play devil's advocate in this idea that you have of the future, right?
Sure.
So we know that there is no system that is completely invulnerable to attack, right? So
Sure.
if we were to have this system in place where you have a voice in your head, what are the alternatives? So what are the consequences of having a malicious attack in this kind of environment?
No, seriously, actually, I'm gonna actually add to that question. So here's an interesting thought. So let's say that everything I said is possible and happens. And so we have this little voice in our brain that's smarter than us, or as smart as us, or whatever. And it just very gently gives us the thought, like let's say you're painting a painting, and it says, maybe a brushstroke here, or maybe a slightly deeper shade of blue there, or whatever. Who gets credit? That example, by the way, I don't take credit for. It's the voice in my head. No. I actually, in preparing this talk, I talked to a lot of my colleagues at Microsoft, and so I want to thank them. But one in particular, Justin Clark, was the one who gives me these questions, right, to think about. So these questions of what happens when you're hacked? Or what happens when you're not hacked, but you don't know who to give credit? I think it's an interesting question, but I don't have an answer. What happens? Some form of schizophrenia is, I guess, what it would look like. And I think it's like Inception, right? Inception was a movie all about this. Is somebody hacked into somebody's brain and gave them this idea at such a deep level that they thought it was their own idea. I was talking to Roger today about that's a lot of my success is relinquishing the egotism associated with the ownership of an idea, planting my ideas into somebody else's brain because I think it's the right idea, but knowing that because of egotism, they're never going to accept it because they didn't think of the idea. But then I shut up about it for about 3 weeks. And then, lo and behold, that idea comes back from another source, and then it becomes the product. So I think that it can be a great tool, is the short answer. I think you're right that hacking is going to happen. I'm not a security guy. So I can't really speak to that stuff. But I think it's a great question. And it opens up, this whole vista of questions, like philosophical questions about where should we stop, what safeguards should we build in. One thing we probably shouldn't do is, let's say that today somebody made a breakthrough and they solved all of these problems. We shouldn't start selling it immediately. We should probably, I don't know what, but we went through a few decades of putting computers out on the internet, and initially they didn't have virus protection and all that kind of stuff. And for a while, people would talk about viruses in this way that I found to be silly and quaint. People would say, oh, my computer's running slow, it must be a virus. And I went through, probably a couple decades of using computers on the internet thinking viruses are not actually a thing that happens very much. And then you surf Reddit for 3 hours, and suddenly, I've got stuff installed, and I feel pretty savvy, right? And I've got stuff installed on my computer, and I'm like, what happened? So the point is that I was sort of lulled myself into a state of complacency, and now, security is a really, really big deal. So, yeah, I think it's a huge potential problem. Anyway, thanks everyone.